Alright, so let's do the lecture number 12. This is going to be just a complete review, so there is nothing to do with the PChem, no derivations for this one right here. I'm just trying to set you up for what's coming for the next couple of lectures, maybe. So, from the last few lectures, we talked about this Gibbs free energy change and then the chemical potential, right? And then by doing so, we derive some equilibrium constant or reaction quotient, right? And in that, we realize that K is dimensionless. And then I think this is from the general chemistry, that pure solid, pure liquid are omitted from this one. I'm going to explain that one too, but let's try to think about why the solvent, like water, is not going to be in there. That's probably the first one, so the pure liquid, right? So before the reaction, you're going to have water too, right? So plus H2O. Liquid. And then the plus H2O liquid, right? So you may actually have this concentration of the H2O here and here, right? But the concentration, because this is a solution, right? Or the solvent, those things doesn't change. It's 55, right? So for the diluted solution, so it's going to be cancelled. And going back to the pure solid, for example, like if you have a platinum solid sitting in the bottom of the reaction container, reaction beakers, I guess, the beaker containing the platinum, that platinum is not going to go anywhere, right? Just sitting at the bottom of the beakers. So all of those things is going to be cancelled, just like the H2O. So that's part of the reason we don't really care about the pure solid or the pure liquid. Alright. The one stuff that you probably need to remember is the KW. It's this reaction right here, because this is pure liquid. It's gonna go away. You have this product only, right? And that's given as 10 to the power of negative 14. And that 10 to the negative 14 is alright for the 25 degrees Celsius, but if you actually change the temperatures, then just realize that sometimes that it changes. So you're gonna learn these things in quantitative chemical analysis, I believe. So that's some other class. Alright, then let's talk about acid dissociations. So if you put the acid into the water, it will create H3O plus, and then whatever the stuff that's the conjugate base, right? And then the dissociation constant is going to be product over reactant, right? And that we actually put that things as Ka. And for the strong acid, the strong definition of the strong acid sets that Ka bigger than 1. And for the definition of the weak acid, Ka has to be less than 1. That's the definition here. And then for the basic solutions, this is the base dissociation reactions. And then once again, product over reactant. We don't care about that one because it's pure liquid. And then Kb stands for the dissociation constant. For this this reaction, it's OH minus BH at the top. That's conjugate acid, and then the original base is at the bottom. And just like the strong acid, strong base, strong acid, strong base definitions, the strong base Kb has to be strictly greater than 1, and then the weak base, the Kb has to be less than 1. And this is also the case for the general chemistry, that you guys need to remember these things right here. The list of the strong acid, strong base. Alright, then the next one. And from the general chemistry, that you can actually add 2 reactions, right? So for example, like if you have this reaction, and then if you have this reaction right here, right? Notice that product become reactant here, right? It's the left hand side, right hand side swaps. If that happens, then the expression also swaps, right? It's always product over reactant. So the Kf right here is same as 1 over Kf is equal to Kr here. When you flip it, it goes to the bottom. And then you can also add 2 reactions to cancel out some of the term and then get the new reactions. And that new reaction will have the equilibrium constant, that is a multiple of K1 and K2 here. All of these things, again, that's covered in the general chemistry, so if you have a hard time catching up, please pause the video and then try to understand it. There is nothing really PChem about these things here. So this is just an example. You have the Kb is given for this reaction right here, and then you're trying to find Ka for this one right here. So we're gonna use this formula to swap it, which is that goes to right here, right here, right? And then that goes to right here. And then you add this reaction right here, which is a Kw reaction here, the water dissociation reactions. If you add it up, these things cancel, that thing cancel, you get these things right here. And that Ka is equal to, because we swapped this one, right? That's 1 over Kb, and then this is Kw. So if you multiply these things right here, then that becomes Ka, right? And Ka turned out to be this one for this particular example. Conjugate acid base pairs, nothing to talk about. And when you actually talk about the conjugate acid base pairs, the if you have certain acid with the dissociation reactions, and then conjugate base have certain its reactions too, right? And then if you add it up, it always adds up to the water dissociation constant. So for that reason, that Ka multiplied by the Kb becomes Kw right here. The important part here is that these are conjugate acid base pairs. So the relationship between the conjugate acid and conjugate base is that if you actually have the 2 of those reactions multiplied together, end up in a Kw. You can pause the video and then try to solve these problems. Alright, so once you're done with that one, then we can also say that there is a polyatomic basis, or the polyprotic basis, sorry, or the is this polyprotic? Polyprotic base here, so polyprotic acid here, that one can donate more than 1 proton, or one can donate more than several OHs. And then getting the concentrations, the simplest one is the H2O dissociations. For this particular case, you have this formation of H plus and OH minus. You from the one water molecule creating exactly the same number of H plus and OH minus. So for this one right here, it's Kw is equal to x squared, right? And we know that Kw is x to the negative 14, so each one of these x has to be 10 to the negative 7. That's the concentration of the H plus. And some other formula that you probably need to remember is the p function right here. If you put anything into this x here, you have p of x, right? Px function minus log, it's a base 10, so it's minus log of x. If you plug in h here, minus log of h plus. If you plug in OH here, minus log of OH concentrations. You can put Ka to get the pKa, minus log of Ka, pKb, minus log of Kb, and Kw, minus log of Kw, which is equal to 14. And let's just put something in here. Maybe we can actually get something. So the Ka, from the several slides before, we actually got this one, right? The acid dissociation. Starting from here, you dissociate into this one, product over reactant, you get this one, right? Slightly rearrange that formula right here so that you can actually see what I'm doing here. pKa right here is equal to, by definition, it's a minus log of Ka, right? And Ka is turned out to be that guy right here, or we can actually put this one right here, right? And then looks like we have a multiplication of that and the multiplication of that, right? So when you actually multiply two things, then you actually have an addition here, right? There is a negative missing here. And because it's a negative, we do actually have some negative on this one too, just because we do actually have negative here. So we got this and that, but take a look at this one right here. That is actually equal to pH, right? So pH, and then I don't like this negative sign, so we're just gonna flip the bottom and top. You get positive of that one. So that formula right here, the pKa, we just try to copy and paste this, copy and paste. That is actually called Henderson-Hasselbalch equations. And it can actually say something interesting here. When the pH is equal to pKa, you have this concentration of that is exactly equal to that one, right? Because log of 1 is actually equal to 0, right? For these two terms to be equal, this has to be 0, right? That means that this one has to be 1. So HA concentration has to be equal to A minus concentrations. When pH is bigger than pKa, then this one has to be negative, right? Then that has to be bigger than that one, right? Because if this is bigger than this guy, right, then this has to be negative, right? Then that one right here has to be bigger than that one. You can actually logically pull through these things right here by yourself. So you can probably figure out exactly where these things are. Starting with one more of the NH3C2COOH. where does this things actually is? It's this one right here, right? That's probably the is this a base or the acid? It's acid because it's going from here to here, right? So that one is there. That one is somewhere around here. I don't really know exactly where it is. Then half mole of OH is added. It's halfway, right? Going from here to here, it's halfway. So it's probably right around here. And then if you put 1 mole of this one, then you are at this point right here. And then if you have 1.5 mole of OH added, then you are right here. And then if you put 2 mole of that, then you are somewhere around here. Oops. And try to pause the video and then take a look at this things right here and then predict the structures at each pH of 1, 2.8, 7, and 10. Remember that the pKa is equal to this formula, right? So you can actually compare pKa and pH, and then you can probably predict which one is having more than the other one. Then you can actually figure out, did I actually lose the H here, or did I actually lose H here, or did I actually lose H here? You can actually think of those stuff in different scenarios. These turn out to be a very important questions for a biochem. I think that's probably good enough.